I want to ask you a question. When you hear the phrase World Oceans Day,
Hmm.
what immediately comes to your mind?
Right. Yeah, it's usually pretty predictable.
Yeah, exactly. If you're anything like me, you probably picture, sea turtles
Hmm.
or maybe preserving coral reefs or some massive campaign to clean up plastic waste.
Right. It's a very specific kind of environmental focus.
Exactly. It's almost always about nature in its purest form. But for this deep dive, we are pivoting to something completely different. I mean, it's totally different, yet equally vital to our survival on this planet.
It really is.
We're looking closely at the concrete, the steel, and the massive human infrastructure that actually touches those waters.
Which is, it represents a really profound shift in perspective, moving from pure environmental preservation to, well, intelligent engineering.
Right.
Because as climate risks intensify, celebrating our oceans also requires us to figure out how we are going to physically survive right next to them.
And that brings us to the core of today's deep dive.
Yeah.
We're looking at this really fascinating piece of research from Roots BIM LLC. It's titled Digital Intelligence for Resilient Coastal Infrastructure.
It's a great paper.
It really is. The mission here is to explore how the architecture, engineering, and construction industry, which we'll call the AEC industry, is fundamentally rethinking how we build and survive on the coastlines.
Using some seriously cutting-edge digital tool.
Right. And it's just such a unique angle. We don't usually associate like heavy maritime construction with the spirit of World Oceans Day. But the technological shift happening in this space is massive.
Totally massive. The AEC industry is realizing that traditional methods of, simply pouring more concrete and hoping for the best, they are just no longer viable.
Yeah, the ocean always wins that fight eventually.
Exactly. The environment is entirely too dynamic now, the threats are too severe, and frankly, the economic stakes are incredibly high. The entire sector is being forced to move toward climate-adaptive digital resilience.
So to really understand why these digital tools are so necessary, we first have to ground ourselves in the sheer scale of human vulnerability on the coasts.
Yeah, the context is everything here.
It is. We need to move from the abstract idea of the ocean as this vast, empty blue space, to the very real places where you, the person listening right now, might actually live, or work, or even just receive your online deliveries from.
The numbers are staggering when you actually lay them out. More than 40% of the global population lives within 100 kilometers of a coastline.
40%. That is wild.
Think about the sheer density of that population. And the built environment supporting all those people relies on a massive interconnected network of coastal assets.
We are talking about global logistics ports, right?
Ports, offshore energy facilities, coastal highways, metro systems, even desalination plants, and sprawling waterfront real estate developments.
So basically the absolute backbone of global economic activity.
Exactly. These physical structures hold everything together.
And all of that infrastructure is sitting right in the crosshairs of an escalating crisis. The research from Roots BIM LLC lays out these threats, and honestly, it reads like an engineering thriller.
It really does. It's pretty intense.
You've got coastal flooding and storm surges, which, we see constantly on the news. But then there are the slow, insidious threats.
Right, the stuff you don't see on the evening news.
Exactly. You have relentless corrosion from salt in the air. You've got saltwater intrusion literally eating away at foundations beneath the surface, and something called wave-induced structural fatigue.
Yeah, wave-induced fatigue is a massive challenge because the ocean never stops moving.
Right.
The constant cyclical pounding of waves against, say, a concrete piling, it might not break it today or tomorrow, but over millions of cycles, it literally tires out the materials.
It just wears it down from the inside.
Exactly. Microfractures form. And once those microfractures open up even a tiny bit, that highly corrosive salt water penetrates the concrete.
Oh, and it reaches the steel inside.
Right. It reaches the internal steel rebar, the steel rusts, and when steel rusts, it expands, which then blows the concrete apart from the inside out.
Oh.
It's a process called spalling, and it is a nightmare for coastal engineers.
I can imagine. And when you factor in rising sea levels, the baseline stress on all these structures is like higher than ever. It's pushing maintenance costs through the roof.
Absolutely through the roof.
Okay, let's unpack this, because this makes me look at the traditional engineering approach with a lot of skepticism. Relying on historical design workflows to build a coastal highway today, it sounds like trying to navigate a modern, changing superhighway using a paper map from 1995.
That is a perfect analogy.
Right, like you just can't anticipate the real-time hazards. The map doesn't show you the sudden flash flood or the shifting shoreline.
Exactly. A paper map from 1995 assumes the landscape never changes. And traditional engineering workflows operate on that exact same static assumption.
They assume the ocean of tomorrow will act like the ocean of yesterday.
Right. Engineers would look at historical weather data, build a seawall maybe a few feet higher than the worst storm recorded in the last century, and, consider the job done.
So they are entirely reactive.
Entirely. They wait for environmental failures to occur before anyone acts. You basically wait for that internal wave fatigue to finally crack the piling.
Or for the storm surge to just overtop the barrier.
Yes,
cliff.
exactly. And then you dispatch a crew to fix it.
But if that historical data is basically useless now, because, the climate is clearly non-stationary,
Yeah.
how are engineers actually predicting what a storm will do to a seawall tomorrow?
That is where the technology has to step in. The research points heavily to building information modeling, or BIM.
Right, BIM. Now, if you are somewhat familiar with architecture, you might think of BIM as just, a fancy 3D digital blueprint.
Which it used to be.
Yeah. But because those old paper map methods are failing so badly, BIM has had to evolve into this multi-dimensional intelligence platform.
It really has. The current iteration of BIM is a completely interconnected data ecosystem. It's capable of absorbing massive, massive amounts of environmental intelligence.
So it's not just drawing lines on a screen anymore.
Not at all. In coastal infrastructure, engineers are integrating BIM with heavy-duty environmental data streams. They pull in Geographic Information System datasets, GIS.
Okay, GIS.
They use LiDAR scans, which map topography with incredible precision using lasers. And they also integrate bathymetric surveys.
Let's define bathymetric surveys for a second, just to be sure we're on the same page, because that plays a huge role here. That's essentially mapping the underwater depth and terrain of the ocean floor.
Correct. Knowing the exact shape of the seafloor is absolutely critical.
Why is that?
Because the underwater topography dictates exactly how a wave will break and how much energy it will carry when it finally hits a structure.
Oh, that makes total sense. A steep drop-off creates a different waves than a shallow slope.
Exactly. So when you combine that bathymetric data with high-resolution drone mapping in GIS, you are feeding the BIM platform a hyper-accurate representation of the physical world.
Okay, wait, so is this just a hyper-realistic video game engine for architects? Are we basically just playing SimCity with better graphics here?
It looks incredible, but if we connect this to the bigger picture, the visual aspect is actually secondary to the analytical engine.
Okay, so it's actively crunching the math.
Yes. By integrating that precise bathymetric data and the spatial geometry of the proposed structure, planners can run hyper-accurate hydrodynamic simulations.
Hydrodynamic. So water movement.
Right. They can simulate the exact interaction between a proposed seawall and a Category 5 storm surge before a single drop of concrete is ever poured.
That is mind-blowing. They're essentially stress testing reality before it happens.
Exactly.
They are calculating exactly how the water will displace, where the sheer force of the wave will transfer into the structure. And even, I assume, whether the shoreline down the coast will erode as a result of building this new wall.
You nailed it. Planners can map tidal behavior, they project long-term sea level rise against the structure's 50-year life cycle, and run wind load analyses.
So you aren't just crossing your fingers anymore.
No. It's about testing a structure's survival in a virtual hurricane, so you can identify the failure points and redesign them immediately. You are designing for dynamic forces rather than those static historical averages.
Okay, simulating a building's design before construction makes total sense. I totally get that. But buildings don't just exist in a vacuum once the ribbon is cut.
No, the real test begins then.
Right. The ocean is constantly moving. It's constantly attacking the structure with that wave fatigue and salt corrosion we talked about earlier. So what happens after the construction phase?
That is the million-dollar question.
You need a tool that tracks this infrastructure in real time. And that leads directly into what the source calls ocean digital twins.
Yes. Ocean digital twins represent a massive, massive leap in how we manage the built environment. A digital twin is a real-time, virtual replica of a physical structure and its surrounding environment.
And it's not just a static model. It is continuously fed by data streams from the physical world.
Continuously.
The source mentions it is fed by the Internet of Things IoT systems. We are talking about sensor networks physically embedded in the concrete, satellites overhead, and global weather systems all talking to each other.
Right. And the convergence of those IoT sensors with artificial intelligence and machine learning is where the true power lies here.
How so?
Well, you might have fiber optic strain gauges embedded in the concrete of a bridge pier. You have acoustic sensors literally listening for micro cracks.
Listening to the concrete.
Yes, and chemical sensors detecting the salinity of the moisture penetrating the surface. The AI analyzes this continuous, massive fire hose of data to identify patterns that a human inspector would never, ever be able to see.
Here's where it gets really interesting to me. Think about this sensor network. It's basically like having a digital voodoo doll of a seaport.
I love that analogy.
Right. If a real-world piling sitting out in the Atlantic Ocean gets slammed by an unexpectedly massive rogue wave, the digital doll feels the exact same stress in real time.
It feels it instantly.
The sensors measure the deflection, and the engineers sitting in a comfortable office hundreds of miles away see that stress register on their screens right then and there.
What's fascinating here is that the voodoo doll analogy illustrates the mechanism perfectly. When that wave hits, the digital twin registers the change in structural tension, and it creates a total paradigm shift from reactive maintenance to predictive intelligence.
Because you aren't waiting for something to visibly break.
Exactly. You aren't waiting for a coastal bridge to rust, weaken, and eventually collapse into the water. The AI detects a tiny shift in the structure's resonance frequency.
Or it flags the microscopic start of corrosion, just based on moisture levels.
Right. You flag the vulnerability incredibly early.
So you fix a microscopic crack today instead of replacing a completely collapsed bridge pier in 10 years.
Which saves lives.
And money. The savings in life cycle costs alone must be enormous. Not to mention the improvement in disaster preparedness. I mean, you actually know exactly how strong your defenses are right before a hurricane hits?
Because the digital twin is telling you the real-time structural health of every single floodgate. You aren't guessing.
It fundamentally rewrites how risk is managed.
It really does. With predictive intelligence, maintenance schedules are completely optimized. You aren't sending diving teams into, dangerous underwater currents for routine visual inspections simply because a calendar says it's time to look at the bridge.
Right. You only intervene when the data tells you there's an actual anomaly.
And you intervene with pinpoint, localized accuracy.
Okay. Having established how this predictive AI and digital twin supersystem works technically, I really want to know what this looks like when it's deployed out in the real world.
Sure, let's ground it.
The source breaks this down across several different sectors. Let's look at smart ports and harbors first, because they are essentially the hubs connecting the ocean to the land.
Ports are incredibly complex logistical nodes, and a BIM-enabled smart port integrates the structural health data with operational data.
So it's not just about the concrete.
No. The digital twin tracks the cargo movement systems, the navigation channels, and the energy consumption analytics, all in one unified dashboard.
That sounds overwhelming.
It would be for a human, but the AI handles it. By monitoring the structural health of the docks alongside the logistics data, port authorities can reduce operational downtime dramatically.
Wait, how does that actually work in practice? How does structural health directly integrate with cargo flow?
Okay, imagine a massive container crane operating on a set of rails along the dock.
Got it.
The sensors might detect that the underlying concrete supporting those rails is experiencing abnormal settlement, maybe shifting by just a few millimeters due to tidal erosion underneath.
Okay, so the foundation is getting slightly washed out.
Right. The AI flags this immediately. The port authority can then look at the cargo schedule, which is also inside the digital twin, and schedule a targeted repair during, say, a 48-hour window of low shipping volume.
Oh, wow. So they fix it before it breaks, and they do it when no ships are waiting.
Exactly. Minimizing economic disruption entirely.
And from those ports, you naturally bleed into the waterfront cities that surround them. We're talking about flood-prone urban areas facing growing climate risks. The source talks about using BIM integrated with environmental platforms to design adaptive drainage systems.
Adaptive drainage is a fascinating application of this tech. Instead of static pipes of a fixed diameter that rely entirely on gravity, which is how we've done it forever, these systems use the predictive power of the digital twin.
So the pipes are smart.
The whole system is. The AI monitors incoming storm data, tidal swells, and even the current soil saturation levels of the city's parks.
Wait, so it's actively managing the water levels. It's not just a passive drain sitting there waiting for rain.
Exactly. The system actively operates smart gates and pumps.
Oh, that's wild.
Right. If a major storm is 36 hours away, the AI can preemptively lower the water levels in urban retention zones and canals. It basically designs the city to act like a giant sponge.
So it creates capacity for the incoming rainfall before the first drop even hits the ground?
Yes, which drastically reduces urban flooding. And the simulations can also dynamically update emergency evacuation routes based on which neighborhoods the model predicts will flood first.
That is incredible engineering.
Right.
But I have to ask, and this is a bit of pushback here, all this technology sounds wildly expensive, and it seems highly focused on protecting expensive human real estate and cargo.
That's a very fair point.
Does this actually help the ocean we're supposedly celebrating on World Oceans Day?
Right.
Because building a massive, highly censored concrete seawall to protect a luxury waterfront development doesn't inherently sound, well, green.
It's a great question. And the tension between developing coastal infrastructure and preserving the marine ecosystem is something the AEC industry is actively wrestling with right now.
So how are they addressing it?
What the Roots BIM research points out is that sustainability is now a major engineering parameter. It is no longer an afterthought.
It's baked into the math.
Exactly. You cannot build a truly resilient port if its construction destroys the local marine ecosystem, like a mangrove forest or a natural reef.
Because those natural elements actually protect the coastline.
Right. Removing those natural wave breaks actually accelerates coastal erosion against your shiny new structure.
So the built environment and the natural environment are literally structurally dependent on each other. You can't just pave over the ocean and expect it to hold.
Precisely. Modern BIM workflows integrate sustainability metrics directly into the physics and design process. Engineers conduct embodied carbon analysis now.
Meaning they calculate the carbon footprint of the materials.
Yes, evaluating the total footprint, the mining, the manufacturing, the transport before anything is even purchased. They utilize what are called environmental product declarations, or EPDs.
How do EPDs integrate with the structural resilience side of things? Like, how does a green certification actually interact with the digital twin?
An EPD provides verified data about the environmental impact of a specific material, say a new type of low-carbon marine concrete.
Okay.
The engineers input that specific EPD data into the digital twin. They simulate not only its structural durability against wave fatigue over 50 years, but also its leaching impact on the local water quality over that same time.
That is seriously impressive.
Mm.
So BIM allows them to balance structural resilience, operational efficiency, and environmental reporting frameworks simultaneously.
All at the exact same time.
You can actually measure whether your new smart port is going to change the tidal flow in a way that creates a dead zone for marine life.
Yeah.
And you can adjust the physical design in the simulation until the environmental impact is minimized.
It really is about coexistence now, not just conquering the coastline.
And that mindset carries over beyond just the coastline, right?
Definitely. The offshore energy sector relies on this exact same principle of minimizing physical footprint while maximizing efficiency.
Right, because building out in the open ocean is a whole different beast.
It is. When you are building offshore energy platforms or complex subsea systems, it is high-density engineering in the middle of a totally hostile ocean. BIM allows for extreme clash detection during the design phase.
Clash detection being the process of making sure two different systems don't accidentally occupy the same physical space in the blueprints.
Exactly that. Ensuring an electrical conduit doesn't physically intersect with a high-pressure valve in plans.
Because fixing that mistake out on the water would be a nightmare.
In the middle of the ocean, fixing a design error like that is astronomically expensive. So the digital twin aids in prefabrication planning on land.
They build it right the first time.
Right. And it provides complete life cycle documentation of subsea assets, which is absolutely critical for maintaining systems in environments where humans literally can't easily go.
So what does this all mean? Think about what this means for you, going about your daily life. Whether you are driving over a coastal bridge on your morning commute, receiving a package that passed through a major smart port, or living in a waterfront city that occasionally worries about hurricane season.
It touches everyone.
It really does.
Mm-hmm.
There is this massive, invisible layer of digital intelligence working behind the scenes. This convergence of BIM, AI, and sensor networks is actively working to keep your physical world intact against an increasingly volatile climate.
And this raises an important question about where we go from here, because the trajectory detailed by Roots BIM LLC points toward a near future that is even more deeply integrated.
How does that look like?
We are looking at the widespread deployment of autonomous inspection robotics. Imagine underwater submersibles that constantly patrol the pilings of a bridge.
Just living down there.
Basically, scanning for microfractures and automatically feeding that data back into the twin without human intervention.
We are moving toward smart seawall systems that can dynamically adapt their physical posture to shifting tidal changes and entirely carbon-neutral waterfront developments.
The ultimate vision is city-scale digital twins. We're moving toward a reality where municipal utilities, transportation networks, emergency services, and marine environmental conditions are perfectly continuously synchronized into one massive predictive dashboard.
A completely interconnected digital and physical ecosystem. It is a stunning vision of human adaptation. We aren't just retreating from the rising oceans, we're using artificial intelligence to learn how to stand our ground intelligently.
It's an inspiring way to look at the future.
It is, but, and I have to bring it back to a slightly terrifying reality here,
Okay.
it leaves me with one final lingering thought for you to mull over.
Oh boy.
If our coastal cities are evolving into continuously updating, deeply interconnected digital ecosystems, where every seawall, every drainage pipe, and every single port sensor is linked through an AI-driven digital twin,
Yeah.
what happens to our physical safety if that central digital nervous system goes offline during a massive, unprecedented storm? How dependent are we willing to become on digital infrastructure to protect our physical reality?